So for number one here, assuming those are all square corners, which I've asked you to do if the drawing's close at least, we have a couple of sides that we need to find. We need to find this side up here. To find that, what I'm going to do is I'm just going to find an overall dimension all the way across there. That's going to be the 4 plus the 16 plus the 4, or 24 inches. Well, then up here, I know that this dimension, whatever it is, plus the 10 has to add up to 24. That makes that 14 inches. Then I need to find this dimension here. To do that, I'm going to find this overall dimension, which is the 2 plus the 20 plus the 8, or 30 inches. And I know that this 5 plus that has to be 30, so this is 25 inches here. Now to find the area of this, I'm looking at it, it would seem to me that it's probably easier to find the bigger rectangle and then subtract out the missing pieces. That bigger rectangle is 30 by 24. So 30 inches times 24 inches is 720 square inches. And then we have to subtract out our pieces that are missing here. So this piece here is 4 by 5.
That's 20.
It's 20 square inches. This piece here is 4 by 8, which is 32 square inches.
32.
And this one up here is 2 by 10.
Makes 10. 20.
Which is 20 square inches. So that makes a total of 72 square inches that has to be subtracted. So subtract 72 square inches, that is 648 square inches as the total area of that shape. For the second piece here, you could argue that there's 3 sections there, the half circle on top, the rectangle in the middle, and the half circle on bottom. Well, before we're done here, I'll actually show you that it can actually be done in just 2 sections. But anyway, first thing we need to know is what this distance is across here. To find that, we're going to find these distances. Those half circles are on the same end, on the ends of the same rectangle. They have to have the same radius, which means the difference between the 16 inches and the 24 inches has to be split evenly. Well, the difference between, what happened there? Give me just a second. I got a new computer here, so we've been having some issues getting it set up. There we go. So the difference between 16 and 24 is 8 inches. We split that evenly between the two. That makes each of them 4 inches. So that means our radius of that half circle is 4 inches. Makes this 8 inches all the way across. So to find the area of this, shape 1 there is a rectangle that's 8 inches by 16 inches, or 128 square inches. The second shape I'm going to do is going to be to take both of these half circles and move them and put them together to make one full circle with a radius of 4 inches. So the area of that one full circle is pi times 4 squared, otherwise known as 50.24 square inches. So our total area is found by just adding those together. 178.24 square inches is the area of that. So I was able to take, not only cut that into smaller pieces, but to take some of those smaller pieces and put them back together to simplify calculating the area for the rest of it. Number 3 over here actually involves the same shapes as number 2. I have a large rectangle here that is 8 by 16. Come on. Or 128 square inches, just like we did on the other one. But in this one, the half circles are not adding onto it, they're being cut out of it on the ends. So we have to subtract the area of that full circle, that pi times 4 squared, which is 50.24 square inches. We subtract that. You get 77.76 square inches of area for that one. So we can cut them apart, and sometimes we put pieces back together to shorten our calculations. But I want you to try this one. Find the area of that triangle for me. So if you recall from yesterday, there's something called Heron's formula, sometimes referred to as Hero's formula, for finding the area of a triangle when all you have are the 3 sides. To find that area, find the perimeter. Well, the perimeter for a triangle is pretty simple. We just add up the sides. So 7 plus 17 is 24, plus another 20 is 44 inches. And then here on, I'm defining something called a semi-perimeter, called S, which was just the perimeter divided by 2. So 44 inches divided by 2 is 22 inches. So then the area was found by taking the square root of that 22 inches, that semi-perimeter, times that semi-perimeter minus the shortest side, so 22 minus 7, times that semi-perimeter minus the middle length side, so 22 minus 17, and the semi-perimeter of 22 minus the longest side, which is 20 in this case. We have the 22. 22 minus 7 is 15. 22 minus 17 is 5. And 22 minus 20 is 2. So now we have to take the square root of that. I don't have my calculator up here. So 22 times 15 times 5 times 2. 57.45 we get as our area. Those were links were in inches, so that is square inches per area. Like I mentioned yesterday, that Huron's formula is a very useful tool, because there are a lot of times where we know the three sides of a triangle, but we don't necessarily know where a right angle is, and finding a right angle to one of those sides, an altitude to one of those sides, would be a lot of work. So being able to just use those sides of the triangle to find the area of that whole triangle really is a very useful thing to have. Okay, so let's get this thing rolling here. What we want to do today, we want to look a little bit closer at these circles. And we're going to be looking at some of the pieces of those circles. So let's review what we know about circles already. We know that this is going to get old, sorry. Every time I get a new computer, it takes a few weeks to get the settings set up so everything works the way it should. So there's an object called a chord, which is a line segment that has its endpoints on the circle. Then there is an object or an item called a feature called the diameter. That is just a chord that contains the center of the circle. So then our first major relationship is between the diameter and the radius. The diameter is equal to twice the radius, or the other way around, the radius is half the diameter. We talked about the circumference being the distance around. And that circumference is found as pi times the diameter, or 2 times the pi times radius, because 2 times radius is equal to the diameter. And of course, the area which is equal to pi times the radius squared. So if we have a circle where we know that it has a diameter 12 feet. The area of that circle is pi times 6 squared. Where did we get the 6 from? Well, the diameter is 12. Area is pi times radius squared. So that 6 is half of the 12. That comes up to be 113.04 square feet. The circumference of that circle would be pi times 12. Pi times diameter is all it's going to be, which is going to be 37.68 feet. That's just a length, is all that is for a perimeter. But what if I don't want the full circle? We did examples of this the last couple of days. One example was a quarter of a circle. And if I wanted to find the area of that quarter circle, I was just dividing the area of the whole circle by 4. Well, first, let's give you... Sorry, trying not to get irritated with it. First, let's give this a name here. The name of this is a sector. Basically, a slice of the circle that we're going to find the area of is called a sector. It's basically a pi wedge out of that whole circle. The area of a sector can be found from the area of a circle. Like I said, we could just divide by 4 like we did before, but let's do this. We know that that is a 90-degree angle there. So to find that area, back up there again, sorry. So to find that area, we are looking at the area of the whole circle, which was 113.04 square feet. But instead of dividing by 4, we're going to do this. We're going to multiply by 90 degrees over 360 degrees. Now you'll notice 90 over 360, that is 4, or 1/4. But we can do it this way. It means that we can find it for any central angle on that sector. So we get 113.04 divided by 4. We get 28.26. That is, of course, square feet. This piece out here, that portion of the circumference of the circle, is called an arc. To find the arc length, okay, this is getting irritating, sorry. Find the arc length, the length of that arc. We'll take the circumference of the whole circle, which was the 37.68 feet times, again, that's a 90-degree angle to the center there. We're taking 90 degrees out of the 360 degrees for the whole circle. So 37.68 times 90 divided by 360 gives it, that is 9.42 feet. That is the length of that arc. So let's take a look at an example here that's just the arc rather than having the full circle. So let's say that we know that this here is 20 degrees. And let's say we have 12 inches for the radius. Now, by knowing that both of those sides are 12 inches, that assures us that this is a sector of a circle. Find the sector area. We first need to find the area of the whole circle. So that A with the circle down beside it like that means the area of the full circle. That's going to be pi times 12 squared. So 3.14 times 12 squared is 452.16. That's in inches, so this is square inches. So to find the area of the sector, so the A with that little sector drawn in beside it is the area of the sector, we take that area of the whole circle, 452.16 square inches, and we're going to multiply. That is 20 degrees out of a full circle would have been 360 degrees. So take our 452.16 times 20 divided by 360. We get 25.12 inches. That is the area, inches squared, I should say. That is the area of that sector. Now, if I want to find the arc length out here, I will need to find the circumference of the whole circle, which will be pi times diameter, which would be 24. If the radius is 12, the diameter is double that, 24. 3.14 times 24 gives us 75.36. That's in inches. That's the distance around the whole shape. So our arc length how any computer I use survives the first couple of weeks is beyond me. I always have a great urge to throw them up against the wall the first couple of weeks until we get the settings ironed out. So the arc length, sorry, I'll try to withhold my frustrations. So the arc length is that total circumference, 75.36 inches, times that central angle is 20 degrees out of 360. So 75.36 times 20 divided by 360 gives us 4.19 inches of arc length. Well, there's another feature of a circle that we have not looked at yet. That's called a segment. This piece colored in out here where it's a chord across the circle. Here's our chord across here. That piece that is cut off on the circle away from the center by that chord is called a segment. And for this example, I'm going to give you let's say that this here is 8 inches, this is 8 inches, and this segment is also 8 inches. The reason that's important is knowing that that segment is 8 inches tells us that what we have here is an equilateral triangle. And one of the facts about an equilateral triangle is all of the angles are 60 degrees. Well, the important one for us is this one right here. That angle is 60 degrees. To find the area of a segment, we take the sector area and we subtract the triangle area. So here, our sector area that whole thing, that sector area, is going to be the area of the circle, pi times 8 squared. That'd be the area of the whole circle, times, I'm going to do this all at once here, 60 degrees over 360. So 3.14 times 8 squared times 60 divided by 360 gives us 33.49. So the area of that sector is 33.49 square inches. That's the area of the whole sector. Well, now we need to go back and find the area of that triangle here. That's this piece, so that we can remove it. We can cut it out, subtract it. Well, that is a triangle that has sides of 8, 8, and 8. So the perimeter, 8 inches plus 8 inches plus 8 inches is 24 inches. So it gives us a semi-perimeter, 24 inches divided by 2, which is 12 inches. And that gives us a formula for the area of that triangle is the square root of 12 times 12 minus 8 times 12 minus 8 times 12 minus 8, since all three sides are 8. So that area, square root of 12 times 4 times 4 times 4, which gives us 27.71. .71 square inches for that triangle. So the area of the sector, or the segment I should say, is that sector of 33.49 minus the 27.71 square inches, of course. Which is 5.78 square inches of area. That is the area of the segment. So to find the area of the segment, there really isn't anything new there as far as concepts. It's just combining a few of the concepts we've already learned together to do one problem. The last thing we want to talk about today, I want to talk about those chords a little bit more. We looked at chords cutting off a segment there. Let's look at two chords in a circle that intersect. So if I have two chords that intersect in a circle, if I know that this chord gets cut into pieces that are 4 inches long and 9 inches long, if I know one of the pieces of the other chord, I can figure out what the second piece is. If I know that this piece is 3 inches long, one of the rules about a circle, one of the quirks about a circle, is if two chords in a circle intersect, they cut themselves into pieces that have equal products. Remember, product is multiplication problem, the result of multiplication problem. So that means in the green there, we have 4 inches and 9 inches. If we multiply those together, 4 inches times 9 inches, and of course that gives us 36, 36 square inches here. That has to equal what we get on the other side. the other chord, I should say, we've got 3 inches times that unknown length, x, has to multiply up to be 36 square inches. So that's telling us that that unknown length has to be 12 inches, because 3 times 12 is 36 square inches. So that has to be 12 inches of length. This is actually a very powerful little rule, especially in construction, because you run into things all the time. Let's say you've got an arched doorway. You have a 36-inch wide doorway. And you're asked to install an arch over the top of it. And that arch they want to have try this again. That arch we want, you gotta be kidding me. One more time. So that arch is going to have a rise of, what do I want to do there? Let's say it's 6 inches. To create that arch, to draw that arch so we know how to cut it out, we need to know the radius of this circle that contains it. The radius like that. Well, to find that radius, we use what we were just talking about as far as those equal chords. I'm going to get rid of this and this here. I don't need those. And that 36 inches, I'm going to move up here. This was 36 inches across there. I am going to extend this 6 inches all the way down, going through the center of the circle. So the 6 inches plus this piece here make a diameter of the circle. I also, another rule of chords in a circle is that if a chord intersects a diameter or a radius at a right angle, it cuts it in half. So this 36 inches is going to get cut in half to 18 inches here and 18 inches over here. So now we know how to find the length of this piece X, because it's going to be 18 inches times 18 inches has to equal 6 inches times the X. So I'm just going to 18 inches times 18 inches. I'm going to divide by this 6 inches here, which gives us 54 inches. X here has to be 54 inches long. So now we know the diameter of the circle. The diameter of the circle is this 54 inches to that far plus this 6 inches. In other words, 60 inches is the diameter of a circle. And of course that gives us a radius of 30 inches. So now we can take a piece of string or whatever, cut it at 30 inches, tie a pencil to the end of it, and we can use that then to sweep out that arc so we can cut it out to get it exactly as wanted. Okay, so we're still dealing with that packet that we posted out there yesterday on Blackboard. In that packet, there's 2 sections we're going to work on. Page 156 through 157 deals with trapezoids and perimeters and areas and stuff of trapezoids and parallelograms, applying that Pythagorean theorem to find missing dimensions. And then page 165 to 168 deals with pieces of the circle. Again, it's the gray boxes that have the problems in them and only do the odds. Okay, so with that, I will be on the network here if you want to stick around and do some homework.